All right, so I'll introduce Kayla since Tamika hasn't gotten here yet. So I'm excited to announce Kayla McVey. She is a rising junior at York College, Pennsylvania, and she worked with Dr. Chun-Lei Fan, Ming Lu, Tamika, and Brittany this summer.
Okay, hi, my name is Kayla. So I worked with Dr. Fan this summer on the evaluation of larval survival and settlement rates in the low salinity tolerant eastern oysters. So a little bit of background of why this research was done. There's been a lot of change in our coastal areas, mostly due to climate change and human influences. So with climate change, we see a lot of rising in sea levels and heavy storms. With human influences, we see a lot of loss of infrastructure. So as climate change happens and human influences happen, we'll see a lot more erosion of our shorelines. This research was funded by the Department of Homeland Security, and they have a coastal resiliency program. If you've ever seen like the maps where it's like these places will be underwater in like X amount of years, that displaces large populations of people. So that's why it's been an issue lately with DHS. So the importance of oysters in living shorelines, they remove excess nutrients such as nitrogen and phosphorus very successfully. Reefs remove 7 times more nutrients than watersheds that don't have successful oyster reefs. They also create habitats for crabs and other fish, help them hide from predators. They support the economy and seafood industry with local and state governments, and just overall improve the appearance of the bay and make it look better. So a challenge with this research is the salinity gradient of the Chesapeake Bay. If you look at the little star right there, that's us. We're in the mesohaline region of the bay, but there's a huge gradient. Down at the bottom is the highest it opens up into the ocean. But as you move in, there's more fresh water mixing in. So the salinity goes down almost as low as 0 parts per thousand up in the northern parts and the rivers. But you can find eastern oysters all throughout the bay. So they're all throughout the salinity gradient. Melting snow in the spring months does cause a decrease in salinity, but then as the weather dries out, it gets a lot higher. So it changes throughout the year as well. So a little bit about oyster larvae. I know for me, before I started this research, they're just kind of like an animal that existed. I didn't know what like the beginning stages were. So this research focused a lot on the larval stages. They start out as the fertilized egg, and then they go through the 4 stages of the larval process. They range between like 60 to 300 micrometers, so they're really not very big. And I just wanted to highlight some structures that we focused on. So the cilia, when they're in the beginning larval stages, it helps them swim around and eat. And then as they grow, they get to the pedivelager stage, which is pedi for foot, and they get the eye spot, which helps them orient, and the foot that helps them settle and set on the substrate. The gut, which is what holds like the algae and helps to digest it, helped us a lot as well, because that was a big indication of health. If it was darker, then the culture was healthier. So the first stage of this experiment was the larval survival. We had the 2 lines, the low salinity tolerant and the Maryland wild type, and we wanted to see the difference between artificial seawater at about 14 parts per thousand, and then ambient. We call it ambient because it kind of changed throughout the experiment. It was taken from the cove out here, so it's usually 9.5 to 12. So first we spawned our Maryland wild type and low salinity tolerant oysters. We used strip spawning, which is surgically removing the gametes, and we combined the eggs and the sperm, which allows for more controlled fertilization. And then this was our experimental design. So we had the replicates for both lines and the 14 and the ambient salinity levels. 3 times a week, we would change out the water, we would collect the larvae and measure the survival and growth. That's what they look like under the microscope. Oops. And then this was our data sheet, so we were able to look at the health and track that, as well as get counts and average out the population and size. So this was the results of our larval survival experiment. You can see there's really no steady increase or decrease between any of the lines throughout the experiment. It was highly variable, and it was decided that it wasn't significant to decide whether there was a difference between the 2 conditions. This is the larval growth results. Once again, there was no steady increase, or it should be an increase because they're growing throughout the experiment, but it was highly variable. So it was also decided as not significant for the data collection. The second phase of this experiment was the settlement experiment, where we wanted to see what the settlement rate of the two lines are in the ambient and high salinity conditions. It was a pretty similar setup. We didn't use our larvae that we spawned because there was a lot of issues with the survival. So we kind of wanted to start fresh. So we took the low salinity tolerant larvae from Horn Point Hatchery, and then the Maryland wild type from Piney Point. It was the same with the replicates and the salinity. We just put oyster shells in the bottom of each bucket to allow for settlement. So this is the data collection. Although the means for the low salinity tolerant line were higher 2 weeks post-settlement, there was no significance between the two settlement rates. And then this is 1 month post-settlement. Once again, the means were slightly higher, but no significant difference between them. And then this is a visual. So 7 days post-settlement, they're really tiny, but you can see them on the shells. You can mostly see the dark guts on the oyster shell. And then they grow pretty quickly throughout the experiment. You can start to see color. They get quite a bit bigger. So one of the biggest issues for this experiment was our water quality. There was a lot of contaminants such as ciliates, rotifers, nematodes, other types of algae that we didn't put in personally. And these will outcompete the larvae for space and food. They're usually quite a bit bigger than the larvae. So the bigger organism is going to get food and space, and it's very detrimental to the health and growth of our larvae. We also had clustering during the settlement experiment. So you'll see higher settlement rates in the beginning of the experiment, but as they grow, they're going to outcompete each other for space and food. So when they're all clustered together like that, they start to grow into each other and will have less spat making it to adulthood, which can be a major problem later on. So this was the low salinity tolerant line for the spat counts. The averages were about in the range from like 20 to 50, but the yellow highlighted were spat counts that were high above the average. So that's the clustering that you see. And then the pink was averages that are a good bit below the average for spat counts. And then that was the Maryland wild type. So to conclude this data, the low salinity tolerant line and the Maryland wild type line showed fairly similar survival, growth, and settlement throughout the experiment, but it was highly variable within each culture, so you're not able to conclude any significance with the data. One thing is that our salinities were fairly similar to each other. 10 and 14 is not that far off. So if we were to do future research, we could do a more drastic difference between the salinities. So like 5 and 20, we might see more differences. Contaminants was likely the cause of the variability. It can be very detrimental to the health. But overall, the best method that we believe in looking at past research is taking native oysters from that area that will be acclimated to that area of the salinity gradient and using that to repopulate and restore the oyster reefs. So I'd just like to thank my mentors, Dr. Fan, Tamika, and Brittany and Amanda, as well as the fellow interns and the Pearl staff. And then any questions?
Back to your seat. On Zoom yet. You explained it so well. No questions for you.
Okay, I'll kick it up. Let some questions in the interim, but maybe I missed this, but so you use the 14 parts per thousand for the artificial seawater. You're exploring, one of the things you're exploring is how well the low salinity tolerant line does, compared to the other line.
Right.
I'm curious why you might not have used like a lower level of salinity to, isn't that ultimately a big part of the point, is to see if this low salinity tolerant oysters can survive at like, problematic levels of salinity, like 5 or 8 or something? Like what's the thought process behind that?
So the 14 is more of like a control. We know that Eastern oysters usually prefer 15 to 20, so 14 might be even a little low, but since we did use oysters native to this area, the ambient, which was supposed to be the low salinity, ranged from about 9.5 to 12. So that would be great for future research. If we did 5, that's a really low salinity. See if there is a difference between the low salinity tolerant and the native oysters.
Thank you.
We have a question from Zoom. Are there any environmentally healthy ways to reduce or eliminate potential parasites who pose risks to the growth process?
It's definitely tough since they are so small to filter them out of the water. Just, I guess, getting a higher quality of water filtration would help. But obviously that's expensive and not always attainable. So.